This is it. This lesson is kind of the culmination of the whole unit. We do have one more lesson that comes up after this, something called Doppler effect, but it's just sort of a little topic to complete it, where vibrating air columns kind of pulls together all that we've been talking about and some more stuff I got to go over to sort of basically, yeah, it highlights, it's the culminating, it's the big topic of the unit. What we just finished was standing waves. Standing waves kind of are the theory of how stringed instruments work. It's a little bit more complicated in reality, but things like a guitar string. The guitar string vibrates following standing waves theory, making high notes, low notes. Basically, as the guitar string vibrates, it makes the air inside the guitar, the air around it vibrate, and the vibrating string triggers a vibration in the air that we hear as sound. Similarly, wind instruments are based on standing waves in the air column of the instrument. So guitar, it's the vibrating string that makes the sound wave. If you blow through something like a clarinet or a flute or even over the top of an empty glass bottle, you get the air inside there vibrating. That's what makes the sound wave. It is the cool culminating topic, but to get there, just to make sure it sinks in nicely, we got to backtrack. And I'm going to go over some things just to make sure it really clicks before we get to actual standing waves. One thing that's going to come up over and over and over again today is this connection between frequency and wavelength. We know this universal wave equation that came up earlier, V equals F lambda. We're going to use that a lot today. If we know the speed of the wave, so the V, if we can do some math to figure out the wavelength, remember the Greek letter L is the wavelength. From those two, then we can figure out the frequency. Or really, if we knew any two between speed, frequency, and wavelength, we can calculate the third. Okay, what I'm saying here in this blurb, I'm going to slide over, so read through that, is when we deal with sound, the speed of sound doesn't change unless we change the air the sound is in, and we don't do that. We're just going to talk about air with a particular speed of sound in the air. We're going to talk about more specifically about the speed of sound before we get going too much farther, but usually the speed of sound doesn't change. So if the speed of sound doesn't change, if the speed of sound is a constant, then really what we're saying is F and lambda have to multiply to make that number. What that means is if frequency were for some reason to be lower, a lower frequency, if we drop the frequency number, then the lambda has to be bigger so that they still multiply to the same number. Or if we do something so that the frequency were to get bigger, a high frequency, then the lambda would have to get smaller so they still multiply to that same number. Or if I kind of rewrite it, so instead of V equals F lambda, if I rewrite it and say F equals V over lambda, the V is a constant. Now we've got more of a math, maybe this makes more sense to mathies out there. There's an inverse relationship between F and lambda. One's on the numerator, the other's on the denominator. That's a classic mathematical inverse. So like in math class, when you're graphing functions eventually, you'll graph y equals 1 over x. That's an inverse. As one gets bigger, the other has to get smaller. So mathematically, logically, there's a connection between frequency and wavelength. We're going to assume that the speed of sound is constant. Low frequency wave, which means a low pitch. So low frequency is going to have a long wavelength. Here, I'll write that out too. Sorry, kind of messy here. And then the inverse, a high frequency sound, is going to have a short wavelength. That's going to come up over and over again as we get into standing waves. Short wavelength means high frequency, long wavelength means low frequency, and vice versa. Okay, so that's the first blurb that I wanted to go over. The second thing, and this is kind of also critically important, sound is what we call a longitudinal wave. It's really air. Let's say we're in a classroom or your house. When there's sound happening, the air in the classroom, the air in your house is wobbling back and forth, creating regions of slightly lower pressure and regions of slightly higher pressure. Here, I'm going to scroll off to the side and I'll kind of talk you through this again as well. Let's go over here this time. Let's say, keep it really simple. Let's say we've got a tuning fork. So I can't draw very well, but this is going to be my tuning fork. Yikes, that's a terrible tuning fork, but let's pretend that's a tuning fork. If you don't know what a tuning fork is, that picture is not going to help you. So maybe Google tuning fork, and you hit the tuning fork with that little hammer thing that tuning forks come with, and these little metal ends of our tuning fork start to wobble back and forth. I'm going to focus on the right side. As this right side of the tuning fork, let's say it moves to the right, it's going to take the air that's in front of it and squish that air up a little bit so that the bundles of air right in front of it are a little bit more squished than they're used to. They don't like being squished more than they're used to, so a split second after they're squished, they're going to pop back and be unsquished. As they pop back and be unsquished, they take the air that's a little bit in front of it and spread it out a little bit more than usual. That air that's spread out a little bit more than usual ends up squishing the air that's a little bit in front of it. That ends up spreading out the air that's a little bit in front of that. That ends up squishing the air that's a little bit in front of that, spreading out the air that's a little bit in front of that. If we had some sort of weird vision or instrument that could read air pressure, if we were to look at a specific location, the air pressure would alternate from high pressure to low pressure over and over again. That's what is happening at any specific spot. The air is alternating from high to low to high to low to high to low. The quicker that alternating high to low pressure happens depends on how quickly the tuning fork is vibrating, and we call that the frequency. If it's a tuning fork made that vibrates at a high frequency, then this high to low pressure wobbling back and forth is going to happen at a high frequency. If I could take a picture, so say we bring the tuning fork and we set up the sound wave blasting across your room. If I could take a picture over time, and see the air pressure, this is what it would kind of look like. We'd have a region of high pressure, HP for high pressure, then right beside it a region of low pressure, then right beside it a region of high pressure, then right beside it a region of low pressure, then high pressure. If we were to graph it, it would kind of like turn into, if we could graph the pressure, it would kind of turn into a sine wave, which is kind of which kind of looks like part of a transverse wave. Oops, sorry. That's what sound waves are. Now, if you were over here, and let's draw you in green. If you were over here, I can draw tuning forks even better than I can draw people. You got an ear on the side of your head. The air right outside your ear, kind of like it did over by the tuning fork, is going to alternate between high and low pressure. High pressure to low pressure, and then back to high pressure. That air outside your ear wobbling from high pressure to low pressure over and over again is going to push your eardrum around. Your eardrum gets pushed into your head for a high pressure, pulled out of your head for a low pressure. That physical movement of your eardrum, there's some really cool biology. The 3 smallest bones in your body are in your ear. They act like little levers. They make fluid inside your cochlea swish around. The fluid swishing in your cochlea is connected to nerves. That sends a signal basically from your ear through these nerves to your brain. When your brain gets those nerve signals, it decodes a couple things. Based on how quickly the high pressure to low pressure change is happening, your brain decodes the frequency or the pitch If it's a high frequency tuning fork, then the high pressure to low pressure alternates very quickly. Your ear's going to hear that as a high pitch. If it's a low frequency tuning fork, then they alternate between high pressure and low pressure a little bit slower. Your brain decodes that as a low pitch. If you really hammer the tuning fork so that the high pressures are really high and the low pressures are really low, we're going to call that a high amplitude. A really high pressure pushes your eardrum, literally pushes it a little bit more distance. The low pressure pulls it a little bit more distance, so there's more range and motion of your eardrum, and your brain decodes that bigger vibration, decodes that as louder. That's kind of a really quick explanation of how sound waves work and how we hear them. My ugly diagram, kind of slide that to the side. So it's all typed in here. The vibrations of these high and low push your eardrum back and forth. You can see in my little diagram, you got the outer ear, your eardrum is kind of in here. This weird snail shell looking thing is with a cochlea. There's fluid in there, and out of the cochlea is this nerve that goes to your brain. That's where the magic happens. If the vibrations are really quick, or what we call a high frequency, your eardrum's fluttering back and forth really quick, your brain decodes that as a high pitch. If the vibrations push and pull your eardrum a large distance, that means a high amplitude. Your brain decodes that as loud. And then kind of a little summary here. We learned that the speed of a sound wave depends on the medium. Loud sound doesn't travel any faster than quiet, and similarly a high pitch doesn't travel any faster than a low pitch. To change the speed of the sound, we somehow have to change the properties of the air. That's a good cliffhanger. We're going to follow up with how we could change the speed of sound in my next little video.